So this was the green chicken exam that almost got me fired from Williams. It was my first year here. I tried something new on the green chicken to try to equalize it between Williams and Middlebury. I put 8 questions, and I said in italics and underlined, if you write up solutions for more than 6 problems, if you don't tell us which 6 to grade, we will only grade the first 6. A lot of students from a school that will remain nameless, but if you flip it, it does look like the symbol for an M&M, just did the first 6 problems. And so whenever you have an exam, what is the first thing you should do on an exam?
Read all the problems.
Read all the problems, especially when all problems count equally likely. The hardest problem may not be the first. The easiest problem may not be the first. You don't know where the easy or the hard problems will be. People could put them in different orders. This is different for the Putnam. For the Putnam, just keep reading A1, A2, B1, B2 for the most part. And then if you want, spend a little bit of time looking at 3, 4, 5, and 6. But for the most part on the Putnam, concentrate on 1 and 2. The Putnam goes to this progression. I don't. So anybody find any problems particularly interesting other than the one we've already done?
3.
Yes, 3?
I like
He spoke first.
What?
Let's do the dots.
Is 3 the dots?
No.
No, I heard 3 first. 3 wins. Loudest voice, first voice wins. So f is a function from 0 to infinity such that f of x plus y is f of xy whenever x and y are greater than 0. Okay. So now I've got to figure out. Okay. So this is 2008, number 3. We have f of x plus y equals f of x plus f of y.
It's f of x.
Oh, f of x times f of x plus y is f of x times y. Okay. If x and y are greater than 0. If f of pi equals e, find f of x for all x. What's the answer? I haven't looked at this in about 6 years. E. Why is the answer E?
Induction. F of pi equals f of pi plus 1.
Okay, that's thinking too hard. So I say find f of x for all x. When you look at this, it seems to be implying that there's a unique f of x. Now this could just be poorly written, and there could have been another reason why I was almost fired, right? But when you look at it, it says find f of x. We lost the green chicken my first year here after a long string of victories. The green chicken went back to Middlebury. Fortunately, I was able to procure a brown chicken from central Massachusetts, and cookies continued after a small absence. But it says find f of x. When it's phrased like this, do you think there could be multiple f of x's? No. When it's phrased like this, it almost seems to be implying that there is a unique f of x. If you just write, well, solution. Note f of x equals e for all x works. Done. How many points do you think that's worth?
Out of 25.
What percent?
Didn't you say if you get the right answer, then you get the right answer?
I think 60%.
So for something like this, whenever you see something like this, you should always put in as much detail as you can. If you can prove it, you should prove it. Okay? So this is probably not the best phrasing. It should be phrased as find all functions, or find with proof all functions, or determine with proof, something like that. To some extent, it's understood in a situation like this that you're not going to just write down the answer. And if you just write down the answer, that is worth some points, but you've got to give a valid argument.
How many points?
It really depends on our mood.
You attach a $20 bill to the exam.
Well, what really matters is one of the Middlebury graders and I were graduate students together at Princeton, and we both have Ohio State connections. So I think the grading is going to be before the Ohio State-Minnesota game, but depending on how that goes, that could affect how we're feeling. So the first thing, though, is when you have a problem like this, try to build up some intuition. Can you look at this? Can you guess what the f could be, or what possible f's? Can you think of any functions where f of x plus y equals f of x times y? And the most natural function to think of is, well, if everything is mapped to the same value, this is going to trivially be true. Well, I know that f of pi is e, therefore, let's say f of x equals e for all values of x. So if you think along those lines, it's not so bad to guess the function that works. But now let's try to prove it. So there was a suggestion to take y equals 1. So this is consider special values. So there are a lot of people who like problems like this. Okay? I will not tell you whether or not I like problems like this. There are times when you have to write exams that you may not want to. There are times when you write exams you do like to. I can't give you any useful information. But a huge number of Putnam problems go along these lines. And you want to choose special values. What would be a wonderful value to take for y? I don't care whether or not you are allowed to. What value for y would you love to take? You'd love to take 0, right? If you could take 0, what would you get? F of x equals f of 0. So if y equals 0 is OK, get f of x equals f of 0 as f of e, I'm sorry, f of pi equals e. This implies f of x equals e. Unfortunately, we can't take x equals 0. But all is not lost. Let y go to 0 from above. Then the limit, as y goes to 0, of f of x plus y is equal to the limit as y goes to 0 of f of xy. This is just f of 0, and this is just f of x. Who's happy about this proof? Okay, if you haven't, okay, what's wrong?
Okay.
Yes? Well, I extend it.
You don't know the limit exists.
We don't, why might the limit not exist?
You don't know about this function.
What do I need to make this argument justified? What do I need to know about f to make this argument? That it's continuous. So this assumes f is continuous. This is a very common mistake people make on Putnam type problems. They're doing something along these lines and they assume the function is continuous. There was a Putnam problem from a couple of years ago with, I think, 4 points on squares. And if you assume that your map is continuous, it's not so bad. But you don't know ahead of time that your map is continuous. So if you were to restrict yourself to continuous functions, then this would be the case. Although you might have a little bit of an issue with, well, what does f of 0 mean? Okay, so we will go back and we'll look at special values. We'll now try y equals 1. So we get f of x plus 1 equals f of x. All right, so what this tells us is the function's periodic. So f, okay. Now what? So we've got f of x plus 1 equals f of x. How does this help us? Comment?
Well, we can start choosing different values, different like small fractional values of y, maybe.
The danger for that is, are we assuming continuity? Does this problem say f is continuous? No. It just says it's a real valued function such that whenever x and y are greater than 0, f of x plus y is f of x times y. So we can immediately get f of 2 equals f of 1. So I haven't looked at this in 6 years, but I have a gut instinct on what to try next. We need to find good values of x and y, right? So we want good values of x and y, and x plus y, and x times y. So again, it's been a long time since I've looked at this, but my gut feeling is I want to choose x and y to make some of the stuff here nice. I'd love to have things equal to 0. I can't do that.
Well, can't you do so if you know like f of 2 equals f of 1,
Mm-hmm.
you also know f of 3 equals f of 2, f of 4
Right.
equals f of 3,
Yep.
and if they're all equal, that means they all have to be the same.
So now I know for all the natural numbers, or maybe the positive natural numbers, they're all the same. Unfortunately, that's not in the same class as E, and that's not all. But we do know that all the natural numbers, all the positive naturals are all equal to f of 1.
We can get that all the rationals are equal to.
You can probably get all the rationals, but I think there's a really good choice for x and y right now. Oh, I'm sorry?
We use f of x as pi. Or can we use x as pi? Sorry.
Okay, so if we chose x as pi, then that would get us a whole chain of things related to pi. Pi plus 1, pi plus 2, pi plus 3, even pi minus 1. But I want to make x plus y or x times y nice.
Should we have x equals pi and y equals 1 over pi?
We could try something like that. More generally, I would say let's just try y to be 1 over x. Right? I can't set x plus y or x times y to be 0, but maybe make x y equals 1. So try x and y such that x times y equals 1. And again, I don't know if this is going to work, but this is a great thing to try. I've got a couple of expressions. I want to make the expressions nice. I already know things about f of 1. So what would I get in this case? I would get f of x plus 1 over x, is f of 1. This is very nice now. We know any number that can be written in the form as x plus 1 over x is equal to f of 1. So now the question becomes, which numbers can be written in the form of x plus 1 over x?
Any rational?
So you give me your favorite number, and let's see if we can write it. So let's say a is greater than 0. Find x such that x plus 1 over x equals a. If we can do that, then we'll have solved the problem. If we can show that no matter what value of a you give me, I can always write a as x plus 1 over x, we're done. The question is, do you think every a can be written in this form, where x is greater than 0? Which a's do you think we have absolutely no chance in hell?
Irrational.
No, not irrational.
Complex.
Things very.
What can you tell me about the size of x plus 1 over x? X is greater than 0.
Be at least 2.
Oh, x doesn't have to be a natural number.
Nope.
Oh.
Right. So x plus 1 over x. The simplest argument is either x or 1 over x has to be greater than 1. So this has to be at least 1. It turns out it's going to be at least 2. So I think what we'll be able to show is any a that's at least 2, we can represent like this. Is it okay if we just do all a greater than or equal to 2?
No. Yes.
Yes. Why yes? What do we know?
This is up first.
It's periodic. So if we have a number that's less than 2, just add 1 to it a couple of times until it's greater than 2. So because it's periodic, it's enough to just do it for a in some range of length 1. We could do it from 3 to 4, from 5 to 6, as long as we can do it in a range of 1. So again, I don't particularly care about this problem, I never have, but I care about the thoughts behind it. And this is an idea that occurs on many Putnams, where you have this kind of product, the sum, you want to choose things so that one of them is nice. Another possibility would be to choose maybe y is 1 minus x. And if x is less than 1, maybe that's something that's nice. Or to choose y to be negative x, where we have no chance of having y be negative x. So again, it's the thought process I care about here, how you would look. So now we want to solve x plus 1 over x equals a. This is the same as x squared minus ax plus 1 equals 0. So x is equal to a plus or minus the square root of a squared minus 4 divided by 2. Okay, so as long as a squared minus 4 is greater than or equal to 0, we're okay. And what do we need for a squared minus 4 to be greater than 0? So if a is greater than 2, we're okay. So as long as a is greater than 2, we're fine. And now for any a greater than 2, we can find an x. Now that we have that x, we go back into here. It's equal to f of 1. So we've now shown that for any a greater than 2, f of a equals f of 1. By periodicity, we can now extend this to all values of a. And now every value is equal to f of 1. Yes?
Do you have to prove that x plus 1 over x equals a represents anything?
Yes. And one of the reasons we have to prove it is because it doesn't represent everything.
Like further than.
Well, this just showed us that if a is greater than 2, we can find an x that's greater than 0 that
Yes.
works. You need to prove this.
Yes, but you don't need to say. Okay.
Right. And now that we have this, then we have to use periodicity. Then use periodicity to get 0 less than a less than equal to 2. So there's several steps here. Everything equals f of 1, including f of pi. And since f of pi equals e, what does f of 1 have to equal? Also has to equal e. Okay. So this is a prototypical example of I give you a function with properties. It's choose special values and keep playing with those special values until you see something. As a nice exercise, it's a Calc 1 problem. Try to figure out what is the smallest value of x plus 1 over x. It turns out that this is going to be 2. And it kind of makes sense. As x gets really close to 0, what's going to happen? It's going to go off to positive infinity. And if x gets really close to infinity, this is going to go off to infinity. So you want to somehow equalize between these two things that are tugging you in different directions. I want x to be large so that this isn't bad. I want x to be small so this isn't bad. Let's make these two terms contribute equally. When does x equal 1 over x? When x equals 1. It's not a proof, but it gives you a heuristic that you would expect this to give you only numbers greater than 2. Okay. Any other questions on this one? Okay. Was the next one the dot problem? Okay, which one is the dot problem? 8. Okay. Show that we can choose 6 distinct points in the plane such that whenever we color any 3 of these points green, there are at least 2 green points exactly 1 centimeter apart. Why do you think we're coloring them green? It's the green chicken, right? Whenever you're reading exams, no, it does not work if it's red. So, be on the lookout for the year, be on the lookout for adjectives that don't really matter. Look out for green herrings, yes?
Can I ask a quick logistical question
Yes.
about the points here?
Mm-hmm.
So the only way to get all points is to do the
Oh, that's true.
problems that
That's true. Here the points are not equally valued.
will that be the case?
No, this year there's only, since the catastrophe of this year, we have gone back to there are always 6 questions, all questions worth the same number of points.
Okay, cool. And
Okay.
you do all 6 questions.
Yes, and you did them all correctly.
Okay.
All right, so we have show can choose 6 distinct points in plane such that whenever color 3 of these green, there are at least 2 points exactly 1 centimeter, 2 green points, exactly 1 centimeter apart. Okay. So we want to show that we can choose 6 points in the plane such that whenever we color any 3 of these points green, there are at least 2 green points exactly 1 centimeter apart. So we get to choose the points, but we don't get to choose which ones are colored green. Right? If we got to choose which points are colored green, would it be easy? Yes. What would you do? Yeah, take 2 points 1 centimeter apart, color them green. When you're reading exams, unlike the Putnam, in a math competition, you can also ask people, is this phrased correctly? If it looks like it's too easy, too good to be true, check. We may not be able to say anything, but at least check. So here, if you were the one who was choosing which points are colored green, well, it's too easy. It's got to be someone else. You're playing a game. So one person is trying to choose the points, the other person is trying to color them in such a way that they can prevent 2 points being exactly 1 centimeter apart. Okay, how far do you think you want to choose points to be? 1 centimeter. What do you think a really good way to start this problem would be?
3 points and adding it.
So let's draw an equilateral triangle. Okay, so if we draw an equilateral triangle, if 2 of these points are colored green, we win. So how many of these points are colored green?
3. 1.
At most 1. At most 1 is green. So the other person is trying to choose 3 points to color green, and there's 6 points total. Okay? So it seems like a good idea to start with an equilateral triangle. The question is now, what do we do? Yes? Okay, so one is to take a second equilateral triangle that shares nothing in common.
Oh, no, let's do it over.
Well,
I made it like a trapeze, or
well, let's
Or you could put it so that those 2 are 1 centimeter.
No, we'll be good with that.
we'll be good with this.
Oh yeah, that's true.
So before we try to get clever, let's try to be careless. All right? Let's just choose 2 triangles. They have no points in common, and we'll say this distance is, in the honor of the proclaim, is 500 miles. Okay? Very far apart. If we choose 2 vertices here to color green, we win. We have to have a 2 green points separated by 1. What about over here? What do we know? At most 1 green. And so now what's going to win the day for us? So what's the math concept? Pigeonhole principle. By pigeonhole principle, at least 1 triangle has 2 vertices colored green. And we win. Okay. So part A, I don't think is that bad for this problem. So the first thing you have to decide is what kind of shapes do you want to start to consider? Well, since the goal is to get things that are 1 centimeter apart that are both green, it seems to make sense to start with an equilateral triangle. That gives us the most possibilities. the next question is, what do we do for extra points? We could draw another triangle, or we could start, forming like hexagons, or forming a lattice by choosing more points that are exactly 1 unit away. All right, so now part B makes it harder. So part A was 5 points, part B is 20 points. So this is still true if now we choose 7 distinct points. So now, we'll make these also 500 miles. And now we put 1 point up over there. And so now, if this is our configuration, unfortunately, we are no longer guaranteed to have 3 points that are exactly 1 centimeter apart.
I'm confused. Couldn't you just pick 7 points within a 1 centimeter radius ball and just say?
No, they have to be exactly 1 centimeter apart.
Okay.
Otherwise, if it was like that, then I could just take.
Okay.
So if the problems ever seem too easy, we've either made a mistake or you're misreading it. Both are almost equally likely. Now, we have tried to have this exam vetted. It's been looked at by, I think, 4 people. So hopefully we've caught all the mistakes. But it is quite possible we have missed something, some phrasing is not clear. If you're not sure, let us know. So unfortunately, this argument breaks down. So now the question becomes, what do we do? So we have some freedom in terms of where we move things. We can still keep these 2 triangles, and we can just change how far apart they are, and we can change where that extra point is. So, okay. I have an idea of where I would like to put things. What would you like to do?
We need to share distances, so 1 point is 1 centimeter from a lot of points.
Good. So it'd be nice to have 1.1 centimeter. Which point would you like to have 1 centimeter from a lot of points?
Multiple points. Not just one.
Well, if you
Because if you pick just 1 point as a centimeter from a lot of points,
right.
then if that point doesn't get chosen, you don't want to be. You don't wanna do
Ah, but look, the only reason this is no longer a solution is because we have this new bad point. If that new point is not colored, what if we know that that new point is not colored? Then we've used 6 points in our old configuration and we win. So one idea is to take our configuration, which was good, and then just show either we color this new point and we color it in such a way that it's got to be near something that shares a color, or we don't color it, and if we don't color it, great, we're wonderful. So my first thought for a problem like this is to try to take this new 7th point, and as you were saying, put a lot of points 1 centimeter from it. What's the maximum number of points I can have 1 centimeter from this and still keep essentially my geometry as before?
6.
But I want to keep my triangles from before. 4. I could do 1 centimeter, 1 centimeter. And this was one of my old triangles. And on the other side, not even closely drawn to scale, so okay, it may not work, but I mean, it's a good thing to try. Okay, so I just want to go through the calculation as to would this work. So if we color this, what would be the danger? We could unfortunately color this one here as well, and this one here as well. And so if we do that, unfortunately, it's possible we have exactly 1 here, exactly 1 here, so we don't have 2 yet in those triangles. Yes?
Could we do like a pentagon and then a point, 2 points inside the pentagon that are equidistant from 2
1,
of the opposite?
3, 4. All right, so these are all 1 unit apart.
Yeah. And then points, 1 point that's like in between those 2 and 1 that's
In between, I mean, I can get 1 point that's 1 unit from 2 of them. Are you trying to get 1 point that's 1 unit from 3 of them?
Does that reach?
I don't know. I'm not sure about a pentagon. You might be able to get it to work, but the geometry there is a little bit different. I'd like to see if we could make this work somehow. This field, unfortunately, it was a natural thing to try putting this here. So there must be a reason why this is 20 points, not 5. But this is a natural thing to try because now if we color this, we lose these 4 points. And these 2 are now causing trouble. Yes?
If you have those rocks how they are,
Yes, excellent.
then there's no reason why you can't just rotate them as separate shapes until you get the distances you want.
So we want to spin this down here, and this is going to sweep out a circle. And just spin this around until this point moves to within 1 unit of this point. Okay? So we're going to lock it over here, and then this whole unit here spins. And so right now, if this is 1, this is 1, you can figure out what the length of that is. Square root of 2. And we're going to keep swinging that until we get to, this is now 1 unit from there. So it's going to look something like this at the end. And now we've got 1 unit. So it goes down to here, maybe. And now we'll have something like this. So that would be our configuration. Does this work?
That was my pentagon.
Is this your pentagon? That is a pentagon. Excellent. So you got to the pentagon in a different way, but excellent. Is this a solution?
But you have 2 better points that are closer than 1 centimeter.
That's fine.
But then,
The problem states I want 2 points that are exactly 1 centimeter apart. I don't care about all the other distances.
Because those 2 points are connected too.
Yeah, they should be aligned.
Oh, yeah, I mean, I'm not drawing all the line. So this one and this one are connected. So if I have 3 from this triangle, I win. If I have 3 from this triangle, I win. If I have this point, the only way I lose, because these are all 1 unit away, is if I have these 2 points, but they're now 1 unit away. So it looks like this is a solution. Why am I hesitant to call it a solution?
those points might overlap.
The points might overlap. You have to show these 2 points are not the same. Once you show they're not the same, then you're done. If you are having trouble showing that they're not the same, what do you do?
I think it's obvious.
You
It follows.
clearly, it readily follows that,
Draw like a very good picture.
right?
Yeah.
Use a ruler.
Use a ruler. Get some rough estimate of where things are.
You don't have rulers. Draw just a really good. Use
Straight edges on
use
the
a straight
paper.
edge. Yeah.
Look, if you can do arithmetic in your head, you should be able to measure in your mind, right? You don't need crutches like rulers.
I skipped all of elementary school. I don't know.
Ah. All right. So you do need to show at the end of the day that these are not the same. So the question is, what's the easiest way to show they're not the same? Well, if they were the same, this would be 1 unit to here. Let me draw it a little bit higher up. And now somehow, if they're the same, the only 2 points that could be the same would be maybe this one and this one,
Can you say that?
or this.
If they were the same, then it would be at the center of the pentagon, and if the edges of the pentagon are 1 centimeter, then the distance is
Exactly. You would have to do some kind of geometric argument like that by saying there's 2 possibilities. This point is the same as that one. This one is the same as that one. Well, if this is the same as that one, then they've completely overlapped. So it can't be this one is the same as that one. The only possibility is this one is the same as that one. And if that is the case now, we would be in the ridiculous situation where we have this has come down to here. We've also got 1 unit away, 1 unit away, 1 unit away. You would be able to get some kind of contradiction from this. But you technically do have to show a contradiction or just write clearly.
You could use a
You could probably use a triangle inequality. There's lots of ways, but I'm just trying to show you, you got to do that last step. And on the Putnam, if they gave you a problem like this, you definitely have to do the last step there. You can try to get away with it. If you can't think of anything better, you can try to do it clearly. I don't recommend it, but okay. Other questions people found interesting? Number 6. Show that there are only finitely many positive integers n such that if d1, d2, dr is the decimal expansion of n, then n also equals d1 to the 1 plus d2 to the 2 plus d3. Okay, so 2008, this is number 6. Show only finitely many x equals d1, d2, dr, then, I guess I'm calling it n. Then n also equals d1 to the 1 plus d2 squared plus d3 cubed plus dr to the r. Okay. Thoughts? Well, first I think we should rewrite n, and then we're having d1 is the largest digit. Okay, so it's equal to d1 times 10 to the r minus 1 plus d2 times 10 to the r minus 2 plus dr times 10 to the 0. So we want to show that there's only finitely many such numbers. So somebody who hasn't spoken yet today, any thoughts on how to attack this? It's okay if it didn't work. What's something you've tried? Yes?
I mean, you could try just combining the D1s, the D2s, D3s, and see if you can get anything out of that.
Okay, what do you mean by combining?
Set those two equal to each other and then start
And then
combining
just
like
move stuff over.
Oh, okay, so we have these are equal. So we get, d1, 10 to the r1 minus 1, plus d2, 10 to the...
Yeah, I don't know.
So it's not a bad thing to try, but the problem is if we start subtracting, it's going to get more and more complicated because the powers of these are all changing. So is there an easier problem to this that we could do? Yes?
I sort of like that the second part of the problem asks, show that any n with this property has a most since 2008. That seems like an easier problem to solve, and if you solve that, you've solved the first part.
Mm-hmm.
Yeah. It's like,
Okay, so part B for 5 points is find such an n with 2 digits. So did anybody find an n with 2 digits? How many possibilities are there to check? Yes?
Like 90.
Not like 90, right? So there's 90 things to try. Worst case, you're not going to get lower than a 5 on this green chicken. You've got 90 things to try. So try it out. Did anybody find any n's that work? So we want 10 d1 plus d2 to equal d1 plus d2 squared. So one possibility is choose values for d2 or d1 and then try to find the values for the other one. Which do you think it's easy to choose, d2 or d1? Would you rather know d2 or would you rather know d1?
D1.
Okay, so if you know D1, then to find D2, you have to solve a quadratic.
Oh, I'd rather know D2.
I'd rather know D2, right? So look, we can write, and this is going back to what was suggested a moment ago, 9D1 equals D2, D2 minus 1. D1 is D2, D2 minus 1 divided by 9. So now, rather than checking 89 things, how many things do we have to check? 10, maybe 9. We can get it a little bit better. This has to be a number that's divisible by 9. There's not that many ways for a number to be divisible by 9. If D2 equals 1, we've got 0, no chance of solution. Can two adjacent numbers both be divisible by 3? No. So I would guess we need D2 to, we need to get an integer. I would guess D2 has to be 9. And then D2 minus 1 would be 8. So I would guess 89. And let's see, 64, oh no, so it's 8 plus 9 squared is 81. Works. So we went from about 100 things to about 89 things to one thing to try. That's not bad. So it's again, and this was going back to the idea from before of trying to combine it, but in just 2 cases, it wasn't so bad. Now, as we get higher and higher up, now we could try to say, well, okay, we found an example with 2 digits. Is there an example with 1 digit? How many examples are there with 1 digit? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Everything works. All 1-digit numbers work. 2-digit numbers, only 89 works. So out of those 89 extra numbers we were adding, only 1 more worked. Are you beginning to feel the finiteness? So we could go up higher and see what would happen if we went up to 3 digits. Can we try to solve that? Let's try to think about what's going on. When we look at the numbers, you want to play order of magnitude games. Approximately how big is n? If I look at this decimal expansion, n is approximately what? D1 times 10 to the r minus 1. The rest of the stuff is minor fluff. It's not going to change it enormously. This is definitely going to be a lower bound for n. So if you want, we know n is greater than or equal to this. What about this expansion over here? What's the largest this expansion could be? Yeah, so we have n is, if I look at the other way, is going to be less than or equal to 9 plus 9 squared plus 9 cubed plus 9 to the r. How would I estimate how big this is? So one way is to say this is, look, this is less than or equal to, I have r terms. Each term is at most 9 to the r. So it's less than r times 9 to the r. We could do better. What's a better way to estimate this? Geometric series. And so it would be 1 minus 9 to the r plus 1 over 1 minus 9, which is just 1/8 times 9 to the r plus 1 minus 1. This is of size 10 to the r minus 1. If you want, this is greater than 1/10 times 10 to the r. This is at most r times 9 to the r. Which is going to be larger eventually, r times 9 to the r or 10 to the r? Yeah. If you want, you could even write this as 10/9 to the r times 9 to the r. And if you write it like that, now they both have a 9 to the r, and you'll see the 10/9 to the r is going to go much faster. This is growing exponentially, this is growing linearly. The idea is, in order for these to be equal, it can only be equal up to a certain point. So this is the example of looking at best case, worst case scenarios. Best case, how big could n be if I look at it like this? Well, the biggest it could be is if every single d was a 9. Worst case, Worst case is d1 equals 1 and everything else equals 0. What if d1 equals 0? Why don't I have to worry about that? It wouldn't be d1. When I'm writing my numbers in decimal expansion, what year is this? Oh, it's not zeros. Not 2008. Oh, okay. I guess if you're looking at what year is this problem from. If you're either doing what year this problem, which is 2008, or what year are we currently in, which is 2014 on the calendar we use, you would never say it's the year 0000002014. You don't append zeros. So when you're doing an analysis like this, you frequently assume the first digit is non-zero, because if not, you would have met it earlier. And so now we have this upper and lower bounds. They are separated for R large. So once R is sufficiently large, they can't be equal. So if R sufficiently big, 1/10 times 10 to the R is greater than R 9 to the R. Therefore, only finitely many R have a chance. All right, and each R, how many possibilities does each R give us? Each only gives us finitely many. Each R gives less than or equal to 10 to the R possibilities. It's really 9 times 10 to the R minus 1, because my first digit can't be 0. It doesn't matter. I'm trying to prove there's only finitely many. Therefore, this is sufficient. OK, so this would prove that there's only finitely many. Now, the problem asks us a little bit more than that. It asks us to show that any n with this property has at most 2008 digits. OK, so the next part is show any n has its R less than or equal to 2008. Do you think 2008 matters? No. Do you think it matters even a little bit?
No.
Probably should be like 2.
Probably a little bit. Since we just showed that 89 works, and we know the numbers 0 to 9 work, there will be some n with this property. But at some point, there will be some largest value of R that works. So all we have to do is show that if we take R equals 2008, that this inequality is satisfied. OK? Yes?
You instead just showed that like 2009 didn't satisfy it. Would that be sufficient with like a Hasenkos?
Sure. Do you think we need to go all the way up to 2008? Probably not. In terms of how high we have to go, if I can get Mathematica to open up fast enough, I will punch this in. Any thoughts? Do you think by I equals 100 we should be OK? So I'm going to solve 10 to the R minus 1 equals, yeah. All right, and so Mathematica, it's giving us R as 0.1. 10 to the R minus 1. It's saying R equals, right. It's saying R equals 0.1. So another way to do it is I'll plot 10 to the R minus 1 minus R 9 to the R. R goes from 1 to 10. All right, there's some strange typo going on because it's giving me 10 to the R minus 1 is less than R 9 to the R. Although we did make one small mistake. All right. I'll have to check on this because eventually this side is going to be larger than this side. I'm not quite sure why Mathematica is saying that this side is larger. I probably have to reboot my computer. All right, so we will continue. We'll do more of these problems. I think this is the best way to prepare for the green chicken. And then I'll just give you another set of problems to look at for Friday.